Hello everyone, I hope all you are doing very good in your life. Today in this video we are going to try to cover the Heisenberg uncertainty principle and then application of the Heisenberg uncertainty principle. First of all, in this video we are going to cover 2 marks definition along with the equation and 8 to 10 marks derivation. So that's why this is very most important concept. Okay, so don't forget to see everything this video. So let's start with Heisenberg uncertainty principle. Why he said uncertainty? See, as we are talking about microparticle means size is very less or very small, like neutron, proton and electron. Size of the electron, size of the proton, size of the neutron is not been able to see either by using any equipment, any scientific equipment, or else by naked eye. So that's why here electron, for example, let us take it as an electron. So where we will find that electron? Electron usually find around the nucleus, surrounding the nucleus. Electron is going to be revolved. Electron is always revolve surrounding to this nucleus. So that means this electron has an momentum that is m into velocity. Okay, now if here we are trying to find the position of this electron, if I want to find out the position, then it is not possible if the electron under motion, because at this moment is here, at this moment is it may be here, or this moment it may be here. So to find out the position, velocity must become a 0. Okay, velocity must become a 0. When there is velocity equals to 0, then momentum will become 0. If momentum will become a 0, then only we can find out the position of the electron. Or else we can say like this also: if I want to find out the momentum, of any particle, that particle must under a motion. When that particle is under a motion, then it has some velocity v. If that particle is under motion and we can find out the momentum, at the same time we can't be able to find out the position, because of momentum this particle is under motion. So this is what we call it as uncertainty. That's why we said Heisenberg uncertainty principle anta kariteve. For example, let us see the definition part. The position and momentum, as I said, the position and momentum of a particle cannot be simultaneously at a time. Momentum, at the same time position can't be able to find, or simultaneously measured, cannot be simultaneously measured with arbitrarily high precision. So with the precision we will not be able to get that. This is what he tried to explain it here. So what is that? Means, as he said, arbitrarily high precision, he doesn't said is equals to 0. He said most of the time it is highly impossible to say this value. So that means we can write delta x, which is related to the position, delta x is related to the position, delta p is related to the momentum, is greater than or equals to h by 4 pi. So x is the position, p is the momentum, is greater than or equal to h by 4 pi. This is what we call it as Heisenberg uncertainty principle equation. This is the equation for Heisenberg uncertainty principle. In the case of energy and time, uncertainty involved in energy and time representation also there, which is not necessarily necessary, just to understand that. And even though there is a angular displacement and angular momentum is also there for uncertainty principle, and that's why there is two example we can mention. If he asked, I mean if VTU in VTU exam, if he asked, you can mention these two examples, which one is energy and time, and angular momentum and angular displacement. Okay, and this is the main equation for an Heisenberg uncertainty principle. So in VTU exam, he may ask you for 2 marks definition. In that case, you need to write either this definition or this one. Okay, once you written, you must mention this equation. That's it. This is the definition part. Let's see the most important concept or most important thing which in this video is we are going to find out the application of Heisenberg uncertainty principle or non-existence of electron in the nucleus. And so what does it means? Till now we know that whenever we draw the molecule, we simply draw like this, right? So we know that inside this molecule there is a nucleus which is in the center, just little bit bigger one. Draw the nucleus. This is the nucleus. Surrounding to this there is an electron which is revolving around it. Okay, so let's draw that electron also. Now see how you got to know that electron never present inside the nucleus. That is what going to be find out in this application. Okay, so let's start with the derivation part. So first of all, let us consider, and one more thing, this derivation must be derived by using energy equation in a old syllabus. According to old syllabus, by using total energy equation, that equation should not be used. This time from 2018 scheme onwards, energy equation is must to solve this derivation. Okay, so let's start non-existence of an electron in the nucleus. Non-existence of an electron in the nucleus. Okay, before we are going to start this derivation, so let's start to understand the basic information related to the practical application. For example, let us take one radioactive element. Let us take one radioactive element which we are going to place it here. As we already know that this radioactive element is going to radiate three types of radiation. One is alpha particle, where it is always attracted towards negative plate because this has a positive charge, and beta particle, beta emission, where always attracted towards positive charge plate because it has negative, and gamma particle which is neutral, it will not attract charge. So usually what we are saying is alpha particle is because of proton, beta particle is because of electron, gamma particle is because of neutron. Okay, this is three kind of radiation we can observe. Now let us find out the energy which we are going to see when we collected that electron or beta particle on this plate, because negative charge will be developed here, positive charge on a positive plate. So the potential difference we can measure, and that energy will be compared with the theoretical energy. If it is matches, then we can say electron resides inside the nucleus. If it doesn't matches, then electron never exists inside the nucleus. With this, let's start the derivation. Now we need to prove electron exists inside the nucleus. Okay, so let us start. As I said, if electron inside the nucleus, then the beta decay which we calculated the energy, that energy must be 3 to 4 mega electron volt. If the electron energy must be there between 3 to 4 mega electron, then we can easily say electron exists inside the nucleus. Okay, so now let us calculate, or let us see the derivation part. To derive this, we must know the energy equation, where we got energy E is equals to half mv square. This half mv square is the kinetic energy, because electron is under motion. Okay, so half mv square will be converted into p square by 2m by multiplying m numerator in denominator. So we got this equation. Okay, so E is equals to p square by 2m is the equation we got this. Now let's see next. As I said, energy we got is E is equals to p square by 2m. If energy which we calculated theoretically is going to match with this practical, that is 3 to 4 mega electron volt, if matches with this value, then we can easily prove that electron exists inside the nucleus. Let's see what happens. As we know that uncertainty principle equation, what is that? Delta P into delta X is greater than or equals to h by 4 pi. Okay, delta P into delta X. Delta P is the momentum, delta X is the position of the electron, greater than or equals to h by 4 pi. Now what we are trying to prove? Electron is inside the nucleus, right? So we can say this electron, this nucleus radiation, this nucleus has a radiation is about 10 raised to minus 15 to 10 raised to minus 14 meter. So radius of the nucleus is 10 raised to minus 15 to 10 raised to 14 meter. So that means that delta X is smaller than or equals to 10 raised to minus 14 meter, because to stay inside the nucleus, radius must be less. It should not, you can't use greater than or equal to, it must be smaller than equals to this much. Okay, now let us write known part one side, like delta P we need to find out, because we don't know the value for delta P. So known part is delta X, shift to this side, then greater than or equals to h by 4 pi into 10 to the power of minus 14. Now substitute the value, h is the Planck's constant, that is 6.626 into 10 to the power of minus 34. We already know that 4 into pi values, put a pi value, then 10 raised to minus 14. Now if we calculate this one, we'll get delta P is equals to greater than or equal to 0.5 into 10 to the power of minus 20. This much we got the momentum, Now we need to substitute this in this equation. We need to substitute this equation in this equation. But the thing is, here is the delta P and here is P. Now delta P means position 2 minus position 1, sorry, momentum 2 minus momentum 1, then only we can use delta P. For to substitute and to get a value, will take P, will convert delta P into P greater than or equal to 0.5 into 10 to the power of minus 20. Okay, so now you can substitute this value in this equation. So let us see the energy, how much energy we can get. E is equals to momentum square, that means into bracket 0.5 into 10 to the power of minus 20 whole square divided by 2 into m. M means what? M is the mass of the electron. Here we are talking about mass of the electron, that means 9.11 into 10 to the power of minus 31. So if we solve this, how much energy will we get? E is equals to 1 point or greater than or equal to 1.372 into 10 to the power of minus 11 joules. This much energy we calculated, but that energy in terms of joules. Okay, energy in terms of joules. Now directly we can't put it here, so we have to convert joules into electrovolt. So by multiplying E is equals to 1.372 into 10 to the power of minus 11 into 6.24 into 10 to the power of plus 18 electron volt. Now we can say energy is greater than or equals to 85 mega electron volt. So this much energy we got when we are trying to say electron exists inside the nucleus, because we take a condition where we said the radius of the nucleus is the delta x is greater than smaller than 10 raised to minus 14 meter. Then also we got this much energy. Practically how much we calculated? Practically we calculated the value is 3 to 4 mega electron volt. So this is the practical result and this one is the theoretical result. Somehow we can accept it, but see the difference, 3 to 4 MeV and 85 MeV. Huge difference. There is a huge difference. That's why we can say electron never resides or electron never exists inside the nucleus, because whenever we say electron is revolving around this orbital, that means this orbital must have that much energy to hold this electron, and this electron is revolving in this orbital, means this electron must have that much energy to stay in this electron. If we increase the energy, then by absorbing that energy, this electron will go make a transition to the higher state energy level, and if we remove the energy, then electron will come back to the original state of the orbital. So this is how we can say electron never exists inside the nucleus. This is what we learn in the Heisenberg uncertainty principle, and this derivation, nothing but this application, will be asked for 8 to 10 marks definite question. Without fail, you will get 8 to 10 marks definite question along with definition of Heisenberg uncertainty principle with equation. Okay, I hope you got to know what I tried to explain in this video. If you got to know what I tried to explain in this video, hit a like button and share with your friends, and don't forget to subscribe to my channel. With this, let's wrap up the video. Thank you.